Good morning, everybody. I'm Barry Burr, and I'm going to be presenting this morning over a simple model that I've built that deals with crude overhead corrosion parameters. First, there'll be a PowerPoint segment. I'll talk about some aspects of the subject and the model. And then we'll go over to the ProMax model side of it, and I'll discuss the model, how to use it. I definitely appreciate you guys registering and signing in to listen to this. And if anybody's interested in working with us using this model later or giving us, some feedback, we are definitely interested in that. So we're very interested in helping people simulate this area of their refinery and we'll help out and work with you to get this model applied to your refinery if you request that. We're going to talk about crude overhead corrosion simulation, and hopefully that can lead to the prevention of some corrosion and optimization of the operations of that section of the tower. We'll talk a little bit about crude distillation tower overhead corrosion, and then we'll look into this new feature we have in ProMax. It started with the release of ProMax 5.0, which is our ProMax salt deposition analysis. And then we'll discuss the main aspects of this crude overhead simulation using ProMax, that it uses the salt point or the salt deposition analysis, but it's been configured so it's really easy to use. So all you have to do is enter parameters about your system using some blue data input fields that are on the flow sheet. So there's very limited things that we think you will need to do using this model, so it'll make it very easy to use. And then I'll show a few scenarios that I've run on this model to show some effects of different things and different things you can change and see how they affect the key variables of interest. So crude overhead corrosion really results, it's caused by chlorides that come from salts that are not removed in the desalting process. So the crude comes in from storage, it's got some water droplets dispersed in it. This water that comes in with the crude is called connate water, and that connate water contains some various salts. And the main chloride salts are sodium chloride, calcium chloride, and magnesium chloride. But magnesium chloride is the one that really decomposes when it enters your crude heater. When the temperatures in the crude heater, they're high enough to decompose the magnesium chloride, some of the calcium chloride, and none of the sodium chloride. So the sodium chloride just goes down and out with the resid out the bottom of the crude tower. The magnesium chloride will decompose, and magnesium hydroxide, I believe, is what's going to go down and out the bottom. And hydrogen chloride is what will turn into a gas, which will rise up to the tower until it rises to the crude overhead line and then condenses when it enters the overhead condenser. And the first water droplet that forms is going to attract all of this hydrogen chloride and create a very acidic solution with a very low pH that is very corrosive. So one way to counter this is by adding a basic material, a neutralizer, so that when the first drop of water condenses, there's going to, instead of there just being hydrochloric acid, there'll also be another basic chemical like ammonia or some amines or ethanolamines that will help to raise the pH. And that's all very nice. It does a good job of neutralizing the aqueous liquid that forms in the crude overhead condenser line. But the problem is that salts will form. These, like ammonium chloride or an amine chloride or an ethanolamine chloride, is likely to form, and it's in our interest to be able to calculate at what temperature these salts will form as the compositions or as the concentrations of this acidic and basic species, as they rise, it's going to induce salt deposition at even lower temperatures. But we want to calculate that and compare that with our operating overhead temperature, make sure that our operating overhead temperature is higher than the salt formation temperature. We're going to build a model that calculates these key properties and is also easy to configure to calculate these key properties. A lot of the new information, we have some salt deposition temperature parameters for several species, but it's this document here, electrolyte thermodynamic modeling for crude distillation overhead systems. It's this document that contained a lot of data for common neutralizers for hydrogen chloride. So this is a very interesting document. You might want to check it out yourself. The link is at the bottom of the page. So this is the source for a lot of the work that has gone into building this simulation and for testing it. Here's another picture from that document. So it shows sort of the configuration or the schematic of the part of the crude distillation unit that we're looking at. Yes, the document is definitely available in English. So here you see this is a figure title and it's in English. The whole document's in English. It's pretty easy to read and I think very helpful. So I highly recommend you look at this document if you're interested in this subject. Here we're going to be looking at the overhead of a crude distillation tower. So the naphtha distillate product plus any reflux, plus any off gas, and plus any water that's going to condense, they're all rising up as vapors into the top of this tower. And it's this stream that we want to create in the simulation. And then we're going to add some wash water gets added and some neutralizer gets added. So it's after this point, after the wash water neutralizer added, we really want to simulate that stream and calculate what the salt formation temperature would be. And then after that, we want to condense all this material. And we want to find out, number one, what is the pH of the first aqueous liquid droplet that forms? That's a very useful piece of information for us. And then also we want to know what is the pH of the liquid in the boot. And the water boot liquid rate is something that can be obtained from a plant engineer or operations. They are usually able to find out what this flow rate is or get a good estimate from it based on what the inputs, the water inputs are that could cause this water boot liquid. And also this can be sampled and analyzed for composition of chlorides and whatever neutralizer you have, so you can analyze this. So it's from the analysis of this water, we tried to create a blend of HCl, ammonia, and H2S that will produce a water boot liquid of a composition that matches what your measurements are. So that's one of the things that we do in the model. And we also try to make a naphtha that will have the endpoint that you're operating at so that we get a reasonably accurate overhead temperature estimation at the same time. So that this is pretty much the scope of the model that we're going to look at, is this diagram that you see right here. Now in ProMax 5.0, we added a new stream analysis. If you're familiar with ProMax and you use it, you see that there are several analyses that you can add to a stream. And this stream, you see there are several other analyses, but one of them is called the salt deposition analysis. And it is able to calculate the salt formation temperature for several different salts and pure components. In this case, I've selected the salt monoethanolamine chloride to have its salt point calculated, and then also just the pure component H2S. This is the temperature at which solid H2S would form, which is not going to happen, but it's something that we can calculate. So you just add this analysis like any other stream analysis, and then this pull down here allows you to choose from a list of possible salts, and you could pick the salt that you're interested in calculating the salt point for. And then whenever the stream executes, it'll tell you what the salt deposition temperature is for that particular salt. If it's the highest temperature, it'll list that as the key salt, and then show up here at key deposition temperature. This is the salt deposition temperature that you are most concerned about, the one that's from this key salt. Now, this does not calculate the salt point from a mixture of, like, it would not calculate the salt point of some mixture of hydrogen chloride, hydrogen sulfide, and ammonia or monoethanolamine. It would not do that. It's only going to calculate the salt point for a pair of salts. Here is the list, currently the list of salts that we have salt point parameters for, correlation parameters for. And the ones that are starred are ones that I've regressed from the reference that I showed you earlier. So these are salts of hydrogen chloride with various bases. Here's monoethanolamine. We're going to look at this one a lot more. So this monoethylene chloride, monoethanolamine chloride is the salt we're going to look at in our little study. And these with the stars behind them, they're not available to you if you have just installed ProMax 5.0, but there is an XML file that I've edited to add the equations and parameters for these. And I can send this XML file to you and tell you where to place it in your File Explorer directory. And when you place it there, then ProMax will have the ability to calculate that salt deposition analysis for these starred salts. From that paper, there were data for salt points versus concentrations of hydrogen chloride, and in this case, MEA. So here you can see sort of what I did. I found the compositions as a function of the inverse of the salt point temperature, and I plotted these, and I used the slope and the y-intercept from this regression, and I placed them into this equation, and this is the format of that salt deposition.xml file. So there is the names of the molecules. There's an equation number that we use for all of these salt deposition equations, and then here are the locations where you add here's the y-intercept, and here is the slope for that I obtained when I was performing this regression against the data in that publication. So this is sort of the process that I went through to get the coefficients for these additional salts. And in the course of working over this in the last couple of days, I do think that I'm going to have to review this and retune it for something I missed. So I do think these numbers are going to change slightly. I don't think they're off by a lot, but I do think I'm going to have to rework all these fits and come up with a new salt deposition.xml file. So in the model that we're going to build, or that we're going to study, there is a few properties that we're going to determine from the simulation. So the purpose of the simulation will be to obtain the hydrocarbon dew point, your water dew point, or the temperature at which the first drop of condensed aqueous liquid appears. And we'll calculate the salt point temperature, and also the pH of the boot water, or the water, the aqueous liquid that's in the water boot, and then the pH of the first condensed aqueous liquid. So these are the things we'll calculate in the model. What we need from the user, what the user needs to supply to make this model work, are the endpoint of your naphtha, the rate of the naphtha and the rate of the reflux, overhead pressure, condenser pressure, and condenser temperature. And we also need the flow rate of the boot liquid, and any neutralizers we need to know. Like if you're adding ammonia, I think this is really going to probably be removed. We won't we won't look at the addition of flow rate addition of neutralizers. We're going to more look at the composition of the HCl and H2S and any neutralizers in the boot liquid. So we need to know that information. And the model that we're going to use, it's already been built, and it's a template ready to be configured to suit your particular refinery, is this model here. It comes in 3 different flow sheets. There's the making the naphtha flow sheet. So we want to make a naphtha that has the right endpoint, and then that will give us the right overhead temperature when we flash it to the tower overhead pressure. So we're going to, in this make naphtha side, all you do is you enter the endpoint of your naphtha in this blue text field, and that's the only user entry required. The next flow sheet is where we prepare the overhead vapor stream, the combined overhead vapor stream. And all these blue text fields are fields where you just click it once, you type the number that represents your plant measurement, and you hit enter, and that loads that value into the corresponding property inside of ProMax. So you never really even have to go into the project viewer for ProMax in order to configure this model. And in this case, the model would be designed to use MEA as the main neutralizer. And I would build another model if you're using ammonia as the main neutralizer. I'd build another model, or some other amine or ethanolamine. I would build another model that would be specific to that one. Even so, if you wanted to take this model and switch it to another one, it's not a really hard job to switch the neutralizer. You just have to change the composition of this neutralizer stream, and then you have to target a solver to look at another stream's composition in the on the next flow sheet. For the most part, your task would be to collect the plant data for your naphtha flow rate, your reflux flow rate, your boot water, the flow rate of your boot water, and then the composition of these species in your boot water. That's what you would need to provide on this flow sheet. This is all done using Ping Robinson, so there's no ionic or electrolytic thermodynamic calculations involved. However, we do transition to another flow sheet which does use an electrolytic package, and we need to do that because we need to calculate the 3-phase electrolytic flash in the condenser, and also towards the right we replicate this, we re-vaporize the stream and then condense it to the point where just a very small amount of liquid forms, so we can find the conditions of the water, aqueous water at the first drop. All of this has to be done in an electrolytic thermal package. And so that's why we're going to a different flow sheet. These calculations take much longer. So this simulation all looks pretty simple, but because we have so many oil components and then the ionic species forming compounds in here, these flashes are actually pretty time consuming. So I think there's 3 solvers for them to all converge. It takes about 5 to 6 minutes for a case to converge because of the slowness of things that go on here. I think I can remove one of the solvers because of something I'll show you later on related to H2S. It just doesn't seem to have very much impact on things. So that solver can probably be eliminated, which will speed up the solve time considerably. And I want to just show you some results from using this model. So first, I want to show that at a constant HCl composition in the boot water, at a constant HCl load, that if we raise the concentration of the MEA, we can see how the salt point and the pHs vary, which is pretty informative. And then we're going to show that at a constant ratio of neutralizer to HCl, as we increase that HCl load, we're going to see how the salt point rises and what the pHs do. And then the last one I wanted to show is that as we hold the MEA and the HCl constant, if we raise the level of H2S, what effects does that have? And I was surprised to see that it actually has very, almost no effect at all. So that's why I think I can remove the H2S solver from the system and speed things up. So here is the case where we increase the amount of neutralizer. So the x-axis is the MEA in the boot liquid, and you see as we increase the rate of MEA, the salt point temperature rises. So it rises and rises and gets closer to whatever your current overhead temperature is. So if it keeps rising, it's eventually probably going to hit your overhead temperature and create a salt forming situation that you really don't want to encounter. But you can also see at the same time, as you increase the amount of neutralizer, that the pH, especially of this first aqueous liquid drop pH, when you have just 10 ppm of MEA, your pH is very low. So that's a corrosive liquid that you don't want forming. But then as you increase the amount of MEA that you're adding, so that your boot liquid has a higher MEA content, you see that at some point the pH of the boot liquid starts to rise a lot, so you're no longer in a corrosive situation. Okay, there's a question about the thermo package used for the ionic species, and that was the electrolytic ELR Ping Robinson. It's just one of our it's very similar to the amine sweetening Ping Robinson package. So you could use either one of those and you would get pretty much the same results. Here we see that as we add MEA, the model is telling you, as it should, that the salt point temperature is going to rise, and also that the pHs of the first drop liquid and the boot water are going to rise as well. Things that make sense. The model should behave in this way. Our next scenario that we run, we are changing simultaneously. We're holding the ratio of MEA to HCl at a 2-to-1 ratio, but we're raising both of those simultaneously as we go along the x-axis. And you see that as the total amount of HCl plus MEA rises, the salt point temperature also rises. So that means the more salt that you don't remove from your desalter, the more salt that enters the column and enters the heater, converts to HCl, the more of that happens. And if you suitably neutralize it, the higher your salt point is going to go. So this means that you really want to remove the salts in the desalter, or else you're going to have more problems with salts forming or low pHs of condensed water in your overhead system. If you don't remove the salt, you're going to have in the desalter, you're going to have more severe problems in your overhead system, shortly thereafter. So this is confirming that, and that the model is able to pick this up. The last scenario I'm going to show you is that, H2S is the other acid that is often measured in these boot waters, and people talk about it. And I wanted to see what does our model say is the effect of adding, holding the HCl and the MEA concentrations constant, but then adding H2S from a low level to a high level. And our model is saying that it really doesn't have any, of course, it would not have an effect on the salt formation temperature for the HCl and MEA salt, because that calculation only cares about the concentrations of HCl and MEA in the overhead vapor. It doesn't care about the H2S concentration. So it's an approximation of what happens in reality. But I don't think a salt of anything that involves H2S is going to form, at these H2S concentrations. However, what was surprising is that the pHs don't seem to be affected by the H2S compositions. It's the HCl and MEA seem to be by far the most significant variables affecting the pH of the boot water and the first condensed liquid. So that's all I have in the presentation of the PowerPoint presentation. Okay, if ammonia is used as a neutralizer, how does it interact with these other components is a good question. So in this case that I'm showing right now, MEA is the neutralizer, but you could have MEA and ammonia appear in the boot water. And for the electrolytic calculations of the pH, I think we would be very accurate at calculating the composition of the boot water and therefore the pH of that. But if ammonia and MEA are present, there's going to be two possible chloride salts that could form. There's an ammonium chloride salt that could form, and there's a MEA chloride salt that could form. So what our salt point analysis or salt deposition analysis will do is it'll report the salt deposition temperature for ammonium chloride based on the partial pressure of ammonia, and the partial pressure of HCl in the overhead vapor stream. And it will also report the salt deposition temperature of the MEA chloride salt based on the concentration of ammonia and of HCl and MEA in the overhead vapor. So it's going to calculate those two salt deposition temperatures without the knowledge that the other basic compound is there. So it's still an approximation. I've made some attempts at simulating or regressing the three component salt mixtures, and it doesn't look very promising to me anyway, at least in based on the kind of models that I saw in the paper that I referred to earlier. There might be some methods for doing that, but I'm not aware of those. Okay, is it possible to simulate different sections within the crude distillation tower itself, taking into account wide temperature differences between condenser and reboiler? I think what you mean is, can we rigorously simulate a crude distillation unit, which of course we can. We do that all the time. So this is, but I didn't want to show that. I didn't want to simulate a full crude distillation unit here when I can accomplish, for this particular problem, I could accomplish it with a much simpler form of model. So I don't want to, but we do simulate crude distillation. Oh, simulate corrosion rate in the tower. Well, I think there would have to be, I would think, to simulate corrosion rate of this form, you would have to be able to predict that there is a free water phase forming on an equilibrium stage somewhere in the tower. And normally we'll have these columns set as vapor, liquid, liquid, equilibrium columns. But usually we only set the condenser stage as being one that could have three phases. ProMax will detect, if ProMax detects that there is a aqueous phase forming on any other stage besides the overhead condenser, we'll get a message indicating that, and we can do some pretty complicated work to basically get reference streams of the phases on that stage, mix them, and then reflash them in a three-phase flash. We could do that, but I think in almost all crude units I've seen, I just never have seen predictions of second liquid phases forming on the stages. There are probably other forms of corrosion that occur on these stages, and maybe there's issues related to entrainment of water that we're not capturing in our separators that assume no entrainment unless you impose it. So normally when we're doing crude distillation work, we just don't see second phases forming on stages other than the condenser in crude units. If you did, we could do some stuff to calculate some properties, but I'm not sure how useful that would really be. In this model, you can see there are these blue numbers. So I can just click on, for instance, this 50 gallons per minute of boot water. I can just click it and type 40, type enter. And now that has gone back Now we're specifying that the boot water flow rate is 40 GPM. And you can see all these other streams have changed from green to maroon, meaning they're no longer solved. They have to be resolved again. I'm going to set it back to 50. Now, each of these compositions, we're trying to force 20 ppm of HCl to form in this boot liquid on the ionic page. So we have a solver on, for instance, this H2S stream right here. So we're adjusting the flow rate of the H2S, and we're trying to drive to that target value of 90 ppm by adjusting the flow rate of the H2S until the concentration in the boot liquid reaches that target value of 90 ppm H2S. So there's a solver on that stream, there's a solver on the HCl here, and there's a solver on the MEA. So there are three solvers simultaneously trying to adjust their flow rates until the boot liquid here has the right composition. So getting those three solvers to converge through this time-consuming electrolytic flash, that's what makes this model take several minutes to run. As I showed you in that scenario, because the H2S is so non-influential, I'm really leaning towards removing, once you have this H2S in the ballpark, and I think it would be easier to just change the mode of the solver from active to disabled and leave the flow rate right there. And I don't think you're likely to see many changes, unless you had a drastic, probably the flow of H2S into your unit is based on how much H2S is in your crude oil. So if that's not changing very much, then this number will be correct all the time, no matter what else you do. Got a couple of questions. With the subcooled reflux, there is a chance for non-equilibrium third phase formation. With a subcooled reflux, and if you don't have the water boot, in our simulation, if you don't add some entrainment specification, you just leave it as an ideal stage flash, the water from the aqueous phase will be removed as a third phase. Now, if you took the condensed hydrocarbon liquid and then further cooled it before feeding back to the stage, then I would see how you would have a chance for some non-equilibrium third phase. That's the way I see it anyway. Next question is, why is ammonia added separately apart from the HCl, H2S, and MEA? That's a good question. I'm probably just going to change that and treat it the same way that I treat the MEA, make it another feed to this mixer that has its own solver trying to match the boot water analysis, because that's really what you probably have. You probably have the boot water analysis, and you're probably less sure of how much ammonia you're actually adding. But if you really knew the amount of ammonia you added, this would be a faster way to solve the model. It wouldn't require a solver, which is what takes up all the time in solving the model. So I guess it's a choice. If you feel you really know the feed rate of your ammonia, it's faster if you leave it here. If you don't know the feed rate of that material, then it's best to treat it as a solver and try to match the boot liquid composition target. Another thing I want to show is that in order to get the right overhead temperature, the dew point of this crude overhead line right here, where we calculate the salt point, well, that temperature is going to be based on the endpoint of your naphtha. So when you set the endpoint of your naphtha and the column pressure, you're pretty much setting the overhead temperature at that point. So the way that we concoct our hydrocarbon that's going to constitute the overhead vapors, it's going to produce naphtha and it's going to produce reflux. But but we don't know the composition of it. So we create a stream that's it's a mixture of heavy naphtha and light naphtha that give us the desired endpoint. So we have a solver on how much light naphtha that we add to this distillation tower, and we adjust the flow rate of the light naphtha until the overhead product has the desired endpoint. And now we don't have the flow rate matching yet. We have the naphtha, we know that, we know the reflux, so we know that the total hydrocarbon flow rate has to be 40,000 barrels per day in this case. So our mixers they have a new feature in them to where, right now we've got 10,000 barrels per day entering the mixer, but I can just delete this parameter called the flow multiplier. I can clear out that, which is by default, it's set to 100%. But when I clear that out, it lets me set the flow rate of the mixer outlet. And then here I can I have a specifier built to have the flow rate of this equal to the sum of the naphtha and the reflux flows. Yes, it's a D86 endpoint in this case. If you had another kind of endpoint, you could just set your distillation curve analysis that you're looking at right here to look at another distillation curve basis, such as TBP. So you can change this pretty easily, or I'd do it for you, no problem. But if you're used to using D86 endpoint, then we would create a stream that targets that. And then see what else is of interest. We apply that salt deposition analysis here. So I'm just going to see if I can get away with just solving a few of these blocks without the solvers. Okay, so here you see before that stream is calculated, these are empty, but now we have the deposition temperature of 235 degrees for the monoethanolamine chloride. If you want to add this analysis, you just press add analysis and choose the salt deposition analysis, and it will add this analysis. And all you have to do is select the salt that you want to salts to be calculated, and those appear. All of your available salts will appear in this list right here. You just pick the ones that you want to have calculations done for. All right, what is the composition of the light and the heavy naphtha? For that one, I just took some very basic. I used our crude oil library, and I think I took the Brent light naphtha and the Brent heavy naphtha. I believe that's what I used. The heavy naphtha, I can't tell after I choose the oil from the oil library and then rename it. I can't really tell what it came from, but I seem to recall that it was Brent heavy naphtha and Brent light naphtha were what these were defined as, and then I could create some mixture of those will have a 290 degree F endpoint. And that's all I really cared about, was getting a naphtha that had an appropriate endpoint. And I think that's going to be a good enough estimation. Okay, so yeah, that's how we add the salt analysis. And then over here on the ionic info, we see that in the environment, we're using the electrolytic NRTL-Ping Robinson. So it wasn't electrolytic ELR, it was electrolytic NRTL. I can't remember why I chose that. I think I had a reason. I can't remember that right now. And then the last thing is when we calculate this first drop, we are finding your setting. Let's see, I am now pressure, temperature. That's not what I expected to see right there. I've got to revisit this. Well, I think I picked a temperature that was just underneath the Yeah, the water dew point minus 0.2 degrees F is the temperature I'm running this flash at, so that it produces a very small amount of water. So that's how I produce a very small amount. If I tried to go closer than this 0.2 degrees F as my criteria, then I was unable to reliably calculate this flash. It was getting too hard to calculate, and I wouldn't always necessarily get a first drop from which I could get a pH analysis from. Okay, so that's the discussion of the model that we're using. So you can see that it's easy to configure. So if you've got a crude unit, you'd like to perform a similar analysis on your system, then it's very easy to get from just asking me for the model to uh, having a running simulation, so long as you know all of this information. Yes, if you're interested in working with us, please contact me. My name is Barry Burr. If you want to, you know, contact me, anytime, and we'll start to work on your crude overhead system. I'd really like to do that. Thank you very much.